Hollis. I am the head of research and development of Aragon SA and R&D SME in Greece. So today my presentation is about our main contribution to the iProd project, which is in the field of complex simulations workflow optimization using evolutionary algorithms. So in general, what do we refer to as simulation flow optimization in any product development process? And this is not only referring to articles themselves. We are dealing with model development, model simulations, model testing, real tests conducted, and etc. So it's a broad range topic, and it can be not only in one organization but across many actors simultaneously or in other fashion. So in essence, workflows are always designed to achieve processing intents of some sort, such as physical transformation, service provision, or information processing. Of course, a simple example might be, as we show here, in weather forecasting, where you have, of course, the resource monitoring, data collection, processing, analysis, the development of physical models, numerical models for predictions and simulation of predictions, and the remaining processes with statistical post-processing, statistical interpretations, etc., until you get to your end goal, where what is the forecast you see every day on the news. So, in the frame of iProd, because we deal with the product development process, of course this involves a very significant element where the product itself, starting from requirements, a range of requirements, is translated eventually into virtual models, whether this be finite element, CFD, or both. So in order to improve the efficiency and quality of any product development process, its workflow should be optimized against specific goals, because if one does not manage it well, then it is a waste, not only in not achieving correct objectives in the product to complete the product development process, but also the resources spent which are not recoverable. So this improvement involves the development and application of task planning, which was presented previously by Senaero of Belgium, based on optimization methodologies. Also in this case, that will take into account multiple objectives and constraints of high, medium, and low levels of the workflow at the same time, and not separately. So in order to address workflow optimization efficiency, a two-level approach is used in iProd. As previously said, first is the human workflow presented by Senaero, which represents the higher generalized overview level of the workflow. So this is the top level where you have all the requirements and the job description and planning. And then we go to the simulation workflow, which represents the lower, the more detailed level, going down to the real details of the actual actions or models or simulations to be done in this workflow that is previously represented by the human workflow. So in iProd, the optimization functionality that is provided first goes through the human workflow to generate a draft optimal schedule of simulations to be performed, which is generated in the task planning, and then this is used for the simulation workflow functionality to generate optimal propositions for individual simulations configurations across multiple gates. Oh, sorry. So I will take a moment here to say something in order to explain why we use this loop here as an example. Because at the end of the day, simulation workflow is not always confined to either CFD models or FEM models. It is not confined necessarily within one department of a company. It could be varied across different departments of the same company, or across different actors, either the OEM and suppliers, or OEMs themselves and the end system integrator. So further to that, we also have the issue that these different, in different cases, you can have actors that are of different disciplines. They might be of the same domain, but they are in a different business area. So just as in aeronautics, an aircraft is made of course, the fuselage, the wings, the engines, etc., and its subsystems. So this is just a very long list of different OEMs and suppliers who design and develop different products. So, and further to that, these systems, although developed first by themselves, but then in unison in the integration phase, they eventually feed into each other towards systems in the aircraft. So in this case, we try to give an optimization, a complex optimization loop, a multi-level optimization loop for the design of an environmental control system for an aircraft. And why we use this example here to show this, well, I can just say just one quick word, that this loop represents a new process that was validated in the FP7 project Crescendo of Airbus, and this represents a use case that was developed with Elenia Armaki and the University of Salento. I only say this to say that in the product development process, especially where humans are involved as the users, the product is developed eventually, but one needs to build prototypes and test them, which is also part of iProd. iProd does not only look at the design part and the optimization of design, it also looks at the design of testing for that end product, but also optimize the actual test, the physical test itself, which is a very integral part of any product development process, because there is a very big decision whether to go to build a prototype or not, and the testing and how this feedback to the actual design refinement process. So in this case, to close the loop here, the environmental control system, which was a design and optimization problem, meaning topology and geometrics of the system itself. This was drawing from various issues, requirements, and models, primarily CFD models, temperature, thermal, humidity, and such. So when these models are integrated based on different optimizations that have occurred, design optimizations, you get a total configuration. So the difficult thing is, how do you actually validate a total configuration for the customer, which in this case is the occupants, the passengers, the human, the pilots, and the cabin crew, and the airline overall. So in this case, this brings in a new element and a new process that was validated recently, that to bring human perception into the design loop, in order to be able to say, without building the entire fuselage with the cabin in it and the system, what is the effect on the human insofar as various critical factors are concerned, such as fatigue, health, and such. So I close this parenthesis here just to say that to do this is a very complex process, and it goes across a lot of different players, and it is an interplay between the OEM, system suppliers, other actors who are developing either the CFD or FEM models, and those who conduct the design optimizations, which means for the product, whether it's its layout or its geometry, or both at the same time. So, moving here, we go back to the beginning where in the task planner, specific tasks are determined for each model in such a process, and the overall optimization loop as is. So this is the draft optimization schedule we were talking about previously. So the required simulations are to be run considered for generic settings and are not alterable in general, not referring to the previous one, but optimization in general at large. So with this first schedule, what happens is that, of course, each simulation has characteristics which are initially considered in the human workflow optimization. So this could be the type of model, the level of detail, which is very important because this defines not only resource usage, CPU usage time, computer time, when it is on, for how long such a station is unavailable, the accuracy of the result, which is very important for the validation of results, and of course, as I mentioned previously, the computation time. A cabin CFD model, an integrated one, could be 120 minutes. A cabin FEM for noise and vibration systems development could be 60 minutes. For the actual product, which is the air conditioning system, it could be, the optimization could be around 20 minutes. The power plant FEM, and so far as flow coming from the bleed air, could be 15 minutes. These are random numbers in here. This first schedule undergoes the optimization for its workflow optimization. So as you can see here, all these parameters can be modified to be able to achieve the results that you want, but at the same time not to go down a path of what we call overkill, that you do not, 100% does not necessarily mean that is what is needed, because a solution may have already been found in the optimization loop, which may have occurred previously and is just running, continuing to run until it reaches the supposed 100%, which could be an insignificant incremental performance increase compared to the 80 or 90% solution. So after an optimization of the simulation workflow, which in essence we're not talking about just one simulation, we're talking about, we have a workflow between the different actors who have different models, who are executing different simulations and tests, that not necessarily is linear or sequential one after the other. You could be also planning them in parallel, especially those who take too long to do compared to others. So after such an optimization, you can see here that a comparative result could be is that the original task plan for the simulation, which is shown in orange, versus how you could optimize not only the sequence, the CPU resource time, when it occurs, and especially also such things, physical things as to what computer to run it on. You can alter significantly the simulation workflow process in order to achieve the same or greater results, but in less time or with less resources. So here is an example of this interface, because at one point, because we also talk about simulations and orchestration of simulations across multiple actors, which are not necessarily also in the same physical location, or someone who is on a higher level of overview and abstraction and administration of an integration project or a product development integration project, that we're able to also do this remotely, but also, more importantly, as we discussed in previous presentations, that we do not necessarily need or cannot connect to each actor's legacy systems where they are making these models and conducting the simulations. So you are able through iProd to have a remote way of not only viewing this information, but also processing the task flow with the information you get from the different actors at various locations, and to be able to resend this information back and readjust the process either in the beginning, in the pre-production phase, or during the process of production, because this information always is accessed at the time that you need it. So here you could see that what I was talking about previously, here you could see current workflow, which is the original draft task plan. Its corresponding tasks, of course, which all of these are based on the ontologies that you will see later also in the other presentation. These are broken down also into the workflow elements, because We go down to this level of detail because we also look to see at the end, if someone wants to, they can actually alter the original workflow. I mean, the optimizations always follow and improve the existing workflow, but someone might say in the process, you know something, we found out that some things are really not that critical anymore, so I want to change it completely without starting all over again. I want to continue from a certain point in time already in the process. And the specific simulation configuration, that is these are the commands or the new plans that go for adjusting these tasks. So of course you cannot see these figures here, but this, as I explained, this data that you are able to access and submit, we show it here. So it's remote access, also remote overview, and also remote action sending. And of course, accept or send execution command for this optimization. So to close here the presentation, we present here the easier said than done concept of simulation workflow optimization. We are currently developing in the iProd project, along with a generic example of what simulation workflow is, because at the end it becomes a very complex and abstract concept when you go from organization up to multiple organizations working at the same time, and how in the iProd it forms an integral part of the optimization functionality, the overall of the iProd framework reasoning engine, which is together with a human workflow simulation. So as we said, this cooperation is necessary, and of course, as I mentioned previously, they're both based on evolutionary algorithms to optimize individual simulation parameters and configurations. So it's not just to say this is how we do the simulations, so just tell me how to do it. We can also adjust and optimize the parameters themselves of those simulations, so we go down to the very low level before we go outwards for a specific application, and this is based, of course, on the overall simulation and task requirements. So the end result is to be able to develop the functionality and tool to facilitate application-specific optimization of simulation tasks in the overall schedule produced by the human workflow optimization function. Thank you.